I don't know if you heard Alex, but we're live now. He forgot to click go live.
That's fine.
Hello, everyone. Welcome to this month's Astronomy on Tap. We're coming to you live from a rainy Baton Rouge day. Thank you all so much for coming tonight. We're always happy to have all of the viewers that we do. And we're sorry that was a little hard to find the stream link this time, but we're getting that fixed up right now. We're still using this opportunity to where we're online to bring you some exciting out-of-town speakers that we hope you all enjoy. And we're also happy to have a more accessible online version than we did back when we were in person. And we hope to keep that going moving forward. Today is actually National Day of Women in Science. So conveniently, we have two very lovely women scientists for you today. And before we get started with our talks, we have our usual ground rules. Number one, be considerate in chat. We haven't had any issues with this, but it's always worth saying. Number two, feel free to drop any questions you have for our speakers at any point during the talk in the chat directly. I'll field those to the speaker once the talk is over. Number three, always consider donating to our Venmo and PayPal. We're getting those links put in our description and put in the chat as well. So if you do so, we always like to add some competition to our donations. So this month, we're going to ask you a really simple question, which is, do you think that NASA or SpaceX will be the first to get Americans back to the moon? If you do make a donation, just make sure you write your answer to that question in the memo section and we'll get that logged for you. The fourth and last one is please like this video if you're watching and subscribe to our YouTube channel. Both of those things help us out a whole lot and probably more than you would think. When we get 100 subscribers, we can get ourselves a fancy, unique YouTube link. And I think as of right now, we're at 95. So just if 5 more of you could do it, that would be awesome. So without further ado, we'll move on to today's talks. So our first speaker I'll introduce is a graduate student from the University of Virginia. She's a chemist by trade, but she firmly straddles the line between chemistry and astronomy. She's an author for Astrobytes, which is a great online site where you can find understandable summaries of recent papers in astronomy. She's here to tell us tonight about all of the weird elements and how they came to be. Please welcome our first speaker, Abby Wagner. She wants to get going.
Cool. All right, am I good to share my screen? Assuming yeah. All right, hello everybody. All right, so today the main goal of my talk is to just tell a general story. And that story is going to be talking about the origins of us in the universe. How did we go from a universe that was almost exclusively hydrogen to humans living and breathing on Earth? And if you're lucky enough, drinking beer or wine for this Astronomy on Tap. All right. So like all good stories, this story starts with a bang. And that bang was the Big Bang. Meaning there was nothing in the universe, and then all of a sudden there was everything. And now this very early universe was made up of almost exclusively hydrogen and electrons with maybe a little bit of helium. And so, again, we want to try and figure out, okay, well, how do we go from a universe that is almost exclusively hydrogen and helium and electrons to humans? And to first answer that question, we have to figure out, okay, well, what are humans actually? Like, what are we? A very philosophical question there. But humans are what we like to call carbon-based life forms. And as a matter of fact, all life as we know it is carbon-based. And so what does that mean? It means that our DNA, which is the thing that makes us who we are, it defines our hair color, our eye color, our height, all of our physical characteristics. It also determines whether we're human or a cat or a strawberry. This DNA is what determines everything about our genetic structure and who we are. And DNA is this kind of spiral twisted ladder structure where the sides of the ladder are made up of carbon. So the very backbone of our DNA is carbon-based. And this is why humans are known as carbon-based life forms. Now, carbon is not the only element that makes up our DNA. There's a few others as well, including hydrogen, nitrogen, carbon, and phosphorus, where these atoms actually make up everything within the DNA. And I know this picture here looks really crazy complex because it looks like there's so much going on, all these different atoms and bonds. But in reality, DNA is actually pretty simple. It's only made up of 4 different molecules. That's it. And those 4 molecules are known as amino acids. And so amino acids are kind of the building blocks of life itself. And so a lot of astrochemistry and a lot of astrobiology is trying to figure out, well, how do we get amino acids to be formed in space? And so here I have the 4 amino acids that make up our DNA, and they're thymine, adenine, cytosine, and guanine. If you ever need to say those again, that would be cool. But the question now is, if we're in a universe that's almost exclusively made up of hydrogen, maybe some helium, and a lot of electrons, how do we go from that hydrogen to now having oxygen and nitrogen, carbon and phosphorus that make up our DNA? And that leads us into the next part of our story, and that's, all right, where's the carbon? So after the Big Bang happened, the universe was incredibly hot. It was crazy hot, but it eventually cooled down, and it cooled down to the point where all of the hydrogen and some helium and electrons in the universe were able to clump together and form these giant clouds in space. And so here I have a little cartoon of my atoms in a cloud. And so as these clouds get even colder and the universe itself starts to cool down even more, these clouds collapse in on themselves. And this is a pretty normal physics principle that as something gets cold, the volume decreases. Whereas if something gets hot, the volume increases. And you can kind of think of this, if you've ever seen a scientist blow up a balloon and then dip it in liquid nitrogen or something, the balloon compresses down. But as it sits in room temperature and heats back up, it expands again. And so the same general concept can be applied when we're looking at these clouds. As they cool down and get cold, they collapse in on themselves and they form stars. So the first stars in our early universe, and this is a picture of the sun as a disclaimer, this is not one of the first stars in our early universe. They are what's responsible for creating all of the other atoms and elements in our universe. And they do that through a process known as nuclear fusion. And so if we look inside of the star, or in this case, a picture of the sun, we can see that these early early stars are made up almost exclusively of hydrogen. And now if we get 4 hydrogen atoms and we bring them together, stars are able to fuse these nuclei, the atoms themselves, together, which is why it's called nuclear fusion. And in fusing these together, they're able to create helium. And this process releases tons and tons and tons of energy. And this is why stars are so crazy hot and crazy bright, is because they're undergoing nuclear fusion. So these early stars start to burn up hydrogen to create helium. And so now we're in a universe with a little bit more helium. And as more time goes on, we get enough helium within these stars to where they can start doing the same thing, only instead of combining hydrogen to make helium, they can start combining helium to make the first carbon atoms. So we now have carbon. We now know carbon is produced within stars themselves. And it turns out carbon is not the only element that is made within this nuclear fusion process. As a matter of fact, all of the elements that are in our DNA, including nitrogen, oxygen, and phosphorus, are also made from nuclear fusion within stars. But these aren't the only elements that are made by stars. These stars produce these elements by living, by going about their normal day-to-day business. But when these stars die, they can supernova, they can explode. And when they explode, they make heavier elements, such as metals like iron, nickel, and gold. And these explosions, these supernova, are also incredibly important to the creation of life, because these metals are also important for us to survive. So as an example, iron is in our blood. Hemoglobin is something in our blood that when we breathe in oxygen, it's hemoglobin that grabs onto the oxygen in our lungs and transports it throughout our body. And so if there's a little iron atom in the center of hemoglobin, and it's iron that is able to grab onto our oxygen and transport it. And this is also why our blood is red, fun fact. And as another fun fact, there's actually a crab that lives at the bottom of the ocean that instead of having an iron center in its blood, it has a copper center. So it has green blood, which I think is just wild. But anyways, so stars are what produce all of these elements that we require to create and sustain life. And so if you've ever heard the saying, oh, we're all stardust, that's not just like a cute, like, oh, we're stardust saying. That is, we are stardust. Somewhere in the distant universe, a star died so that we could live. And I think that's just magical. All right. So we have everything we need now to make life, now that the stars have sacrificed themselves for us. And so now the question is, okay, well, how is DNA made now that we have all the components? Well, this is a pretty complex answer. So we're going to come back to the DNA question. And after we also figure out, where does Earth come from? Because first we need a place for our life to live, right? We can't exist in the nothingness of space. So our next part of our story is part 3. How do planets form? So this is a pretty similar process to the formation of the first stars that we already talked about. Only now we're in an older universe that is chemically rich and diverse, meaning we have lots of different atoms and molecules, ices and pieces of dust and grains in space, which I'll explain in just a second. And similar to how our first star formed, when all of these clouds collapse in on themselves, the same thing is going to happen now when we form a new star, only this time we're going to expand on that. And imagine if you're on a merry-go-round and there's a bunch of you and you're all sitting around the edges and someone is spinning the merry-go-round really fast. You feel like you're going to fly off. You feel like you're being pushed away from the center, where the center of the merry-go-round, or maybe the center where the star is forming. As these clouds collapse down, they spin in a similar manner to where some of the gas in these clouds spins around and around and around the center star, and they form a giant dusty disk of gases and ices. In these clouds, these cloudy disks around stars, we call them protoplanetary disks. And that literally means what it sounds like. It's a pre-planetary system that someday planets will form in these regions. And these are objects that we can actually observe in space. So here I have a picture of TW Hydra. So this is an actual image of a planet-forming region in space, which I just also think is super cool. But sometimes artist renditions are a little bit more fun. So here I have a picture of an artist rendition of a protoplanetary disk, where we can see in the center, there's a bright baby star forming, and around it we have this gaseous cloud swirling around it. And so let's look a little bit closer into this disk now, and so we can get a better idea on how planets actually form. So these clouds are made up of, like I said, tons of gases that are now rich in chemistry. They have molecules and atoms and all sorts of other wacky looking molecules in there. But we also have dust grains. And so these dust grains, you can kind of imagine them as being like little pieces of sand in space, only they're like really, really tiny, like a micrometer size, which is very, very small. If you don't know what scale that is, it's very small. Now, these dust grains are made up of carbon or silicon usually, and they're actually produced usually when the star supernovas. So more stars dying to make sure we can live yet again. And so these protoplanetary disks can get really, really cold within the inner regions of this disk. And they get so cold that these gases can stick and freeze out onto the grains and create layers of ice. And it turns out these layers of ice are one of the most important parts that when we start thinking about forming planets and life itself. And so we're going to talk about ice a lot from here on out. But first, we're going to continue going on the planet formation track. So if we had two dust grains in space that were not covered in ice, if they were going at each other and they hit, there was no ice, these dust grains would bounce off. They would not stick. And so they would just keep going on about their day. However, these layers of ice that are able to form on these dust grains make them sticky. And I know that's kind of weird. We don't usually think of ice being sticky, but it actually is. So if we get two dust grains covered in ice, when they collide, they actually stick now, because the different atoms and molecules in the ice, they kind of like realize that they can bond, they can grab onto each other, and so they allow the ice to stick together and get bigger. And so over time, as more and more icy dust grains hit and collide and it gets bigger, we form what's called a planetesimal. And that's basically just a baby planet. It's a very small baby planet. And so these planetesimals, though, they start to have gravitational pull. So as they're flying or orbiting around the central star, they're able to start picking up other gases and dust particles and become bigger and bigger and bigger until they have enough mass to where they actually form planets. And so this is just a general idea on or a general overview on how planets form. And here I have another schematic that will put it in another cartoon fashion that may make it a little bit easier to hopefully visualize all at once. And that's how planets form when a giant gas cloud in space collapses in on itself, forming a protoplanetary disk, where eventually dust grains stick together and collide and form planets. So awesome, we now have a planet for life to live. We have Earth. And so now it's time to kind of come back to that question of, okay, where does the life actually form? Where do the molecules that make up our DNA, the amino acids, where do they come from? And the answer to that is through all of this, as a matter of fact. So chemistry is occurring through all of these phases within the molecular cloud and the protoplanetary disk. And even when the planets are still forming, there's still chemistry going on, forming bigger new molecules. And so the chemistry that occurs within this time frame is what shapes and determines the chemistry that will be available on planets once they formed. And that's what determines whether or not there is enough molecules to form and sustain life. And so it turns out a lot of chemistry happens in the gas phase, but the chemistry that we care about for life-sustaining molecules, like amino acids, those happen within the ice layers of dust grains, which we've already talked about. And so here I have like my general kind of cartoon of the dust grain covered in a layer of ice. And this is a very simplified picture, but in reality, these dust grains are really complex. As a matter of fact, you could get a PhD in studying dust, and you can get a PhD in studying ice. I know people that are. It's very cool work. But basically, there are tons of things going on. So for example, molecules that are in the gas phase can stick to the ice and freeze out, creating more thicker ices. Or if the dust grain gets hotter, so maybe it gets closer to the star, the ices can evaporate, putting molecules back in the gas phase. Light from either the central star in a protoplanetary disk or maybe other nearby stars can drive chemistry to happen within these ices. And not only that, but the gases can bombard the ice, making more chemistry to happen. And so as you can see, these are all very complex. There's a lot going on here and a lot that's happening all at once. But the main takeaway message is that within these ice layers of these dust grains in space is where molecules are forming. And so these molecules, if we remember, the ice layers on dust grains are what allow them to stick together and form planets. And so the molecules that are being made in these ices are, we think, hopefully will be transferred to the planets that will eventually form. So if we consider the dust grain and our idea that these individual dust grains come together to create an Earth, that tells us that maybe these molecules that are forming on these dust grains are delivered to Earth through this mechanism. But unfortunately, the real picture is a little bit more challenging than just a simple step-by-step. In reality, the Earth itself was probably not water-rich when it formed. And so this mechanism doesn't completely make sense because the Earth doesn't have enough water to have done this. As a matter of fact, we think that when the Earth actually formed initially, it was a dry desert planet. And so this is a picture of Tatooine from Star Wars, because I couldn't find a good picture of dry Earth before humans existed. And so how did the ice that carried biologically relevant molecules and the water that filled our ocean, how does that ice get to the Earth? And the answer to that is from comets, we're pretty sure. So comets are formed in the outer parts of our solar system, so really far away. And you can think of them as like either a dirty ice ball or an icy dirt ball. There's basically a lot of dirt and a lot of water. And we've all seen real pretty pictures of comets like this, but in reality, a comet itself actually just looks kind of just like a rock. So this pretty beautiful glowing tail behind the comet is caused when the comet is flying around the sun, and the hot sun is evaporating ice from the comet, and the ice is blowing behind it, causing that pretty tail. And so if we look at what the comet's, the head of the comet basically, we see that it looks more like a rock, an icy rock to be exact. And so what scientists or astronomers and scientists think happened is that the water on Earth was delivered when a comet collided with the planet. And this is significant because not only would this comet have just delivered water, it would have delivered everything else on it too. And as a matter of fact, recently, in the past few years, astronomers have detected a molecule called glycine in the comet 67P. Now, glycine is the simplest amino acid. And even though glycine is not in our DNA, it's not one of the 4 that we need to make up human DNA, it's still an incredibly important molecule. And so maybe when the Earth formed, it was a dry desert planet, maybe like Tatooine. And maybe a comet did come by and deliver all the ice, creating the Earth as we know it. And perhaps also amino acids were delivered when this occurred. I don't know if you all can hear, my cat is like destroying my door, and I do apologize if you hear that. Okay, sorry. Cool, thank you all. All right, so this comet delivered water and amino acids to Earth, probably. So then the question kind of we have to circle back is, okay, if this is how amino acids were delivered to Earth, along with all the water, is how do we go from amino acids to actually this crazy complex structure of DNA? And the answer to that, unfortunately, we still don't quite know the answer to, which will be an exciting day someday when we discover this. But for now, we just kind of have to leave a question mark on it and say it happened at some point in time. And so in summary, I'd like to just put up like another brief overview of like this journey that we walked on, starting with a Big Bang. That the Big Bang created a lot of hydrogen in the universe. And then after the hydrogen could cool down and create stars, those initial first stars, and stars still do this to this day, created more elements, creating a chemically rich and diverse universe that's not just hydrogen, but now has carbon that we need to make humans. And now in this chemically rich universe, we're able to form, protoplanetary disks now, where eventually planets occur, bringing this chemically rich environment with them into the planets. These formed planets, or this newly formed Earth in this case that we're considering, probably got its water from a comet. And maybe when that comet delivered all of that water, it brought with it amino acids as well. And then some way, somehow down the line, those amino acids form the first DNA. And eventually, some many, many years later, DNA is what led to the first humans, which brings us to our current world. So that's all for my talk. Thank you all for listening. I hope you enjoyed this journey.
Thank you, Abby. Really good talk. So if you want to unshare your screen, we can start the questions. But I wanted to start with some questions about you, because I think something that's really important about Astronomy on Tap is that we are humanizing science and sort of showing the human behind the science. So I perused your Twitter and noticed that you described yourself as a self-taught astronomer. Can you tell us about like what you did, how you did it, all that kind of stuff?
Yeah, I don't remember where I said that on Twitter, but I'm sure I did.
There.
Yeah, so I actually come from like a pretty small local small region where like my graduating high school class was like 130 kids. And we didn't teach physics or astronomy in my high school. And so the first time I was ever even exposed to physics was in a college course, which was absolutely wild. And no piece of me had any thought of mind of like, oh, I should do astronomy. Because to me, that was this abstract thing that people did, but I didn't really know much about. Until like one day I was looking through like a chemistry job site and saw astrochemistry, and I had to know what that was. And so I kind of instantly fell in love with it and decided that this is what I had to do with my life. And on a whim, with zero astronomy coursework or background or experience, I started applying to astronomy internships during my undergrad career or during my bachelor's degree. And I just so happened to get a position at the Harvard Smithsonian Center for Astrophysics, where I worked with Ilsa Cleaves, who's now my current research advisor for my PhD. And so that was my first formal experience ever learning any astronomy, was on the job itself. And so a lot of what I had to do and like self-teach myself was I would hear these concepts that people would say. I would write them down in a little journal and then go home and like sit on my bed at night and just Google it in Wikipedia, like what is a protoplanetary disk?
Oh, the power of Wikipedia. I think you touched on something that I think a lot of astronomers kind of know, and maybe people in sort of normal life don't know, which is that and all the sciences are like, you can mix and match them. And like, if you have any sort of knowledge of problem solving, you're going to be fine in any science, and you can pretty much pick it up as much as you want.
Yeah, I would absolutely agree with that.
I wanted to ask you also, what are your hobbies outside of astronomy and chemistry? Do you have any?
Yeah, I am the definition of a nerd.
We all.
So I do play a lot of, I read a lot and play video games, but I think my biggest pastime is I play Dungeons and Dragons, and I am a dungeon master. So I spend a lot of my free time dedicated to making a campaign for my players.
Here's my advice. That could be within arm's reach. No. Well, what other video games do you play?
I would have to say my favorite, it would be probably Horizon Zero Dawn. That one is, in my opinion, probably one of the greatest video games ever made.
It's funny because you can ask someone who plays video games what kind of video games they play, and they will always tell you something different. And it's usually something that you're like, not, I've never played that game. Very interesting. I know that we're in a bit of a weird time, but what would you say a normal day of work looks like for you?
Yeah, I try to wake up relatively early, but pandemic, that doesn't always happen. I usually spend the first hour of my morning looking through all the recent papers that have come out in the past day and trying to find ones relevant to my field. We actually have a journal club that meets every day for 30 minutes, which is really fun because we can talk about all the newest papers and subjects that have come out. If you saw on the news a couple months ago, probably at this point, phosphine was detected in Venus.
Oh, yeah.
That was a grand topic in our research group for quite some time. Okay. And then for the most part, I might have like a couple of meetings, but I usually spend most of my time just trying to do work myself. And for me, that usually means like a lot of coding and a lot of like looking at plots and a lot of fighting Python and Fortran scripts.
Yes, I think we can all agree with fighting Python and Fortran. And then before we move on to the science questions, the most important question, what is your favorite Pokemon?
I thought about it really hard and I decided on Dragonite.
That's a good choice. He's so round.
I know, and he's a dragon. He's a cool one.
Anyways, that's a good choice. Okay. So I'm gonna field you some questions from the chat as soon as I find some. I wanted to commend you on doing a great job hitting so many science fields and subfields all in one talk. I think you mentioned like biochemistry, planetary astro, radio astronomy, all dust astronomy, all that kind of stuff. So definitely good job on that. The first question is from Stephen Dorsher. He asks, is DNA essential for the theory of evolution? And would other forms of maybe, say, silicon-based or not carbon-based life still evolve in such a way? What do you think?
Yeah, so that's a really good question. I can't imagine that life could exist without some form of DNA. I think by definition, as far as what our definition of life is, it requires DNA. As far as the carbon versus silicon-based discussion, that's a really fun one. If you're a Star Trek fan, there's an episode in like the original Star Trek where Captain Kirk and Spock find a silicon-based life form that like spits acid. And I do really like the idea of the possibility of a silicon-based life form. And one of the main arguments behind why silicon could perhaps be a substitute for carbon is because of the unique way that carbon and silicon kind of bond. So carbon likes to form 4 bonds with other atoms. If it doesn't have 4 bonds exactly, it is not happy, it is not stable, it doesn't like it. And so that's why it's so good at like building the structure that makes up our life. And silicon has a very similar bonding pattern to where it can bond in a similar way and it prefers to have 4 bonds. But silicon is a little bit bigger, and because it's a bigger atom, it has more flexibility. And so sometimes if it doesn't have exactly 4 bonds, it's more okay with that. It's not as crazy unhappy as carbon would be. So in my personal opinion, I would be very skeptical of the possibility of a silicon-based life form, but the sci-fi nerd in me is like, yes, I want it to happen.
Related question that is not from the chat, it's from my own brain. Do you believe in aliens?
I think the universe is too big for nothing else to exist, but
I've always gone with too, so yeah. I agree with you on that part. Mars Newman asks, how often does a planetary system form from stars?
Ooh, I wouldn't know like a number off the top of my head for like a rate, but it's common. Like if you look up in the sky and just pick a random star, there's probably at least some form of like disk forming region or planet forming region or disk or something going on around it. If you have the time, you should look up like graphics of detected planets. There's so many wild, different, awesome figures out there showing all the different detected planets around different stars. So it's very frequent.
Okay. Stephen Dorsher also asks, if planets carry amino acids, is there any speculation that they also carry small bacteria or protozoa or something of the like, causing transfer between planets that may then have some divergent evolution?
Yeah, so this is getting a little bit beyond my personal area of expertise, but I have heard this argument before. There's also like, I've seen other arguments that like maybe a comet or a meteor got real close to one planet and picked up an amino acid and then brought it to another planet. But I think overall the odds of that happening are probably low, especially if you would consider like the amount of like biologically relevant molecules that would have to be transferred to be significant enough to produce and carry on life within an entire other system. So I don't know if it would be impossible, but I would personally think the odds would be not great.
Okay. There was a lot of discussion in the chat about everyone's respective D&D characters. So
I'll go look at it.
But Rob Parks also asks, was water deposited by a single comet or by a shower of comets?
Ooh, that's another good question. I actually don't know the answer to that. all the arguments I've heard suggest a single comet, but I'm not sure. I'm sure there's someone out there that has been studying this and would have an actual good answer for that.
What is your research on like right now? Like, what are you researching right now?
Yeah, so I study chemistry and protoplanetary disks. And like, so specifically, I look at how the young star, it emits, basically it has like solar flares, but we call them X-ray flares when it's not our sun. And I study how those solar flares emitted by the young baby star derive chemistry on like a short day-to-day time scale, which is pretty unique because astronomy usually considers like over millions of year time scales, and I'm looking at like weeks.
There's also the important fact if you actually look at how the chemical evolution does, where most astronomers are like, I don't care about that. They're like, I want to see the X-rays. That's it.
Yeah, it hurts. The astronomer's periodic table is hydrogen, helium, and metals.
So good. It's so good. Okay. Okay, so that's all the questions that I have in the chat, but I want to again thank you for your great talk. Wait, do we have one more? Oh, we have one more, and it's a good question, so I'm going to ask it. It's from Cannon Fodder. It says, any recommendations for a fellow 20-something-year-old wanting to follow in your footsteps and get into astronomy despite not having any previous background?
Oh, I love it. I would say, if just start going after it, start pursuing it. It will be difficult. So when I applied for that first internship, I applied to like 6 or 7 different internships, and I got into 2. But those 2 that I got into, one of them was at Harvard. And I even said in my application, I have 0 background, but I really want to do this. And so if you express that enthusiasm and you show that you have like a knowledge base that you're able to problem solve and learn, that's what really matters. So I highly recommend if you want to do interdisciplinary research or switch research fields, that all that you have to do is just do it. So
very inspirational topic to end on. Okay, so we're going to take a quick break for intermission. Before we do, I'd like to humbly ask you again to consider donating to our Venmo or PayPal. Hopefully those links are circling through the chat. If not, I will put them there. If you do, be sure in the comments to let us know your answer to this month's tip war, which, to refresh, is simply who you think will get us back to the moon first, NASA or SpaceX. So we're going to take a quick break, and we'll be presenting you with some fun space trivia, and we will be back in 5 minutes or so, which is going to be at about 7:43. I wish I could end on a round number, but I never can. 7:44 actually is when we're going to come back. So until then, enjoy our space trivia. Hello, everyone. Welcome back. We're going to go straight into our second speaker today. So just an introduction. Our second speaker is a researcher at Arizona, soon to be moving to Hawaii to work at the Gemini telescope. She's actually an LSU alumni, and as such is deeply upset to not be able to sit at the varsity and eat red beans and rice from Chimes. Her house contains more cats than people, and she likes it that way. And she's here to tell us today about what happens when a star halfway explodes. This is my academic sister, Dr. Jennifer Andrews.
All right, let's see if I can get this started. Yes, I would very much enjoy red beans and rice right now, but what can you do? Tucson does not exactly have the best Cajun food, so. All right, and everything looks good?
Yes.
Perfect. Yes, so I was a grad student. I guess it's been almost 10 years now since I graduated, but I try to get back to Baton Rouge as much as possible, which is not very often these days. And that's actually where I did kind of get a job doing dust, since my thesis had a lot to do with dust. So like the previous speaker spoke about, I got my an actual job in dust. So, but I've moved on a little bit from that since then. And today I'm going to talk about supernova imposters, which are basically the eruptions of massive stars. And when the star erupts, it leaves something behind. So it's not a supernova explosion, which is terminal. So before we actually discuss what a supernova imposter is, we should discuss what an actual supernova is. And to do that, we'll start with this really great life cycle of stars. On the left is stars that are less massive, like our sun. And so I'm not going to really be discussing those today. But on the right are massive stars. So these are stars that are 8 to 10 solar masses, 8 to 10 times the mass of our sun, or way higher, all the way up to, we think, maybe 100, 150 solar masses. So giant stars. And if you notice, the circles are a lot smaller on the left side for the massive stars. And that's because the bigger you are as a star, the faster you live. So you live fast, you die young, you burn through your fuel very quickly. And the very basic rule is that, as we were discussing, you form stars, and that's where your planets are formed as well, in your protostars. And then you spend most of your time on what we call the main sequence, which I'll discuss in a second. And then as you start burning more, all this time you're burning hydrogen into helium, and then you start burning helium into heavier elements, which, as was discussed before, we astronomers call metals. And so there's an end life phase that we call the supergiant phase. And then at that point, once it runs out of fuel and can't burn, or it gets down to iron, can't burn that, it explodes as a supernova. So what I'm going to be talking about are stars that have left this sort of normal branch here and are somewhere between burning just hydrogen to helium and exploding as a supernova. And they do weird things, or they have companions that make them do weird things. And just to reiterate, a supernova is a terminal. I'll keep saying this throughout. It's terminal, which means that it is an end phase. Okay, so here we have what we call an HR diagram, which is great. That shows, this is temperature along the bottom, luminosity along the top, so brightness. So as you head this way, you get hotter, and as you head this way, you get brighter. So things that are way up here are bright and hot, and way down here are dim and cooler. I can't say cold because it's not going to be cold. So so the sun sort of lies right around here. And if we look at a 15 solar mass star, so remember, anything over 8 solar masses, we think can become a supernova. So it's a massive star that runs out of fuel, blows itself up, does this really interesting trek as it stays around the same, it starts burning helium instead of hydrogen. And it does this weird, interesting thing where it stays about the same brightness, but it gets cooler. And to get cooler, the way that we handle that in thermodynamics is if you're just as bright, but you're cooler, you get puffier, you get bigger, you turn red. And then, so these are the red supergiants, of which our famous Betelgeuse is one. And then other heavier elements start burning. And there's a lot of things that are happening in this area that make the stars do weird things. They explode, they erupt. There's weird convection happening within the core. We don't know what gets dredged up. It starts losing a lot of dust and mass. It's very unstable at this point. And then eventually it will explode as a supernova. And what's left behind is a neutron star or a black hole. And I think what's really cool, and it's great, this is great to follow the last talk, is this is a cut of what in the inside of a supergiant star is. So like I said, it goes from hydrogen to helium and then helium to heavier elements. So this shows the supergiant star, which would, expand out to Jupiter's orbit if it was placed where the sun is. And while it spends most of its life burning hydrogen, so say for the star 10 million years, it only takes 1 million year to burn through its helium, and then roughly 300 years through its carbon, and then 6 months for the neon, and 1 week for oxygen, and then just a day for the silicon shell before you have an iron core. So this is actually how we're getting these heavier elements that make humans inside the massive star here. And so there's a lot of stuff that happens in this last, 1 million years that can make the star unstable and allow it to almost look like it's exploding. For astronomers sitting on Earth observing, we see something get really bright and we think, oh, it's a supernova. But then we go back later and look and the star is still there. And it just has gotten very bright for a short period of time and has returned to a star that we can observe like we had before the brightening. Oops, okay, that is backwards. So what does a supernova look like? So for instance, let's say we were just looking at this region of sky over and over each night. And then one night we go to the telescope and all of a sudden we see this. So this is what we think is a supernova. And in fact, this was a supernova. The supernova is older than probably most of the grad students here. So this is 1987A. And what has happened is that the star has gotten brighter. And so we go and we take images, we take spectra, we look at it and we say, okay, yes, this looks like a supernova. We keep watching it. It gets fainter. And we're pretty sure that it is. But there are some instances, especially these days, as there are a lot of these transient searches that look at the sky all night long to look for supernova explosions. And we find lots of weird objects that are massive stars that look super bright. And we think that they are supernova, but they're just not quite bright enough to be a supernova. So there's not enough energy to fully explode the star. And then, like I said, when they return back, after a couple of months or weeks or years, it looks like the star before. So it just had a burp, basically, but the star is still there. And that's what supernova imposters are. So I mentioned that we follow it from the ground or from Hubble or various other space telescopes, because we can look in the optical, we can look at the X-rays, infrared, gamma rays, all sorts, because there's so much energy coming from a supernova and from just a giant massive star explosion that we should be able to detect these. And what we do is we take observations every night or as often as possible. And what we'll see, and you'll be able to watch here in this graph, is the brightness changes over time. So as the stars start, the supernova itself is at peak, and then over a certain amount of days, it will slowly decline or quickly decline, depending on what kind of supernova it was, how large it was, if it's surrounded by material, various things like that. And so this is one of the benchmarks we look for to say, okay, this definitely looks like a supernova, or maybe this is just a massive star that is having an outburst. Okay. So to see it sort of in a graphical way, what I have here on the left is this plot shows a bunch of different objects that we have discovered and followed from the ground and space, transients, that they're variable stars that we think are either supernovae or some other type of transition in a star's life. Okay, so we have things getting brighter as you go up the y-axis, and then basically how long it takes to fade, how long we can still see it. And so your bright stuff up here are all supernovae, and including 87A, which I showed for on the first slide. And this is just a handful of picked objects. And down here we have novae and various other objects, which are very, they get bright quickly, but they don't get super bright. And we only really see them in our own Milky Way or very nearby galaxies because they're quite faint. And we catch them quickly and then they're gone and we can't see them anymore. The supernovae, we can even catch them months after explosion and notice that they're significantly brighter than something that was there before. But in between are these supernova imposters that aren't quite bright enough to be supernovae, but are a little too bright to be regular novae. And they are generally bright for long periods of time, and some, this area over here, can be bright for years. And this, we're going to talk about an object in this area later on, in one of the most enigmatic supernova imposters. But to show it graphically, so remember I showed how the brightness changes with time. Let's see if I can actually work there we go. So it fades, it gets fainter, and then levels out. So this mouse is, there we go. So if we look at that in graphical form, a regular supernova would be somewhere up here. So very bright. And it stays bright for a certain amount of days, here, say about 100. Some fainter supernovae look similar, but are less bright. And then around in here, we have these supernova imposters that they get quite bright. They kind of look like supernovae, but we find out later that it was not a terminal explosion, or there's different elements present in the spectra that we take that shouldn't be there if it was a supernova. Or there's other characteristics which make us realize that it was an imposter. Now, one thing to note is that often we don't know that it's a supernova imposter until later. There are still some objects that we aren't sure if it's really exploded or not, because what can happen is, as a supernova explodes, or as a supernova imposter erupts, it can create a nice shell of dust around it. And so it looks like it's completely faded away, but in fact, maybe it's just hidden in dust. So the two main ways where we get these outbursts of massive stars that don't end in supernovae, or sometimes they do, are from strong winds from the star, or binary interaction. Sometimes, and you can have both as well. So they can both cause variability prior to the terminal event. So I made this great little wonderfully well-made cartoon. So one way where the massive star winds can actually create this supernova, semi-supernova looking object is, so remember I said as it gets cooler, gets bigger, redder, but the wind speed is actually of this like the solar wind we have here on Earth from the sun, the star wind, the solar wind of the star, as it gets bigger, the speed is slower. So as you're losing material, what's happening is in the same amount of time, the material, the wind from the star is moving very, very slowly. But then say during this time, the star, some sort of, something happens within interior and it decides it's going to get hotter. It's going to shrink down. It comes back to equilibrium and it becomes a blue star. But as it gets smaller and hotter, the wind becomes a lot faster. And so what can happen is over like a same amount of time period as for the material moving from a red star, the blue star will catch up. The wind from there will catch up to the wind the material that had been lost from the red star. And the shock interaction that happens there can just then create a big explosion or quick brightening. It'll make the star look a lot brighter. And the star itself hasn't exploded. It's just that the material lost from the star has run into previous material lost by the star and makes it look like we've had a big explosion. And in fact, we have some great HST imaging that shows some material moving, and you can see up here the date that passes. You can see material moving outward from a massive star. And it doesn't necessarily show it running into other things, but you can see how some areas are moving faster than others. All right, and now the other way besides the winds are binaries. So there's a quick movie that I want to show that is available. This is a NASA video here that's showing two sort of 15 solar mass stars in orbit around each other. And as time is going on, one of the stars is just slightly more massive than the other. So it's evolving a little faster. Material is being stripped from the smaller one, the smaller radius, to the bigger one. You can't see it until now. And so it's helping the one of the stars evolve a lot faster, right? So all the material that it would normally lose during its regular evolution is being stripped from it super quickly. And so all that's left is just the core. So this star is collapsing on itself, and it's going to eventually go supernova. Bam. And then the companion star now is sucking up basically all of that, a lot of that material. And so it becomes a red supergiant star, and it evolves very fast as well, and it explodes. And so what could be left there are two neutron stars. And also, one thing to mention is that during this whole exchange of material, there can be lots of brightenings. That's just an illustration of what could happen. And so you can have a bunch of times when mass is being transferred over and there isn't a complete explosion, but there's enough material that goes onto the donor star that it brightens. And I mentioned neutron stars because, you know, as you may well know, LIGO Livingston is one of the telescopes that did discover the neutron star collision in the kilonova. And one thing that is often wondered is, how do you actually get two neutron stars orbiting each other? And it's because you start out with two massive stars, or you can start out with two massive stars orbiting each other. So I felt that was very, very, very good to show today, since I think it's the 5-year anniversary of the big discovery of the first gravitational wave. All right, so the rest of the time, I'm going to just talk about the most well-studied supernova imposter, and that is Eta Car, and in particular, its great eruption that happened in the mid 1800s. And so here you can see this is Eta Car. It's inside this nebulosity here, which we call the homunculus, and it's embedded within the Carina Nebula. And unfortunately, we can't see it from the north. This is only a southern target because the Carina Nebula is only seen in the south. But in the 1850s, the mid 1800s, there's a noticeable brightening of the object, and it got much brighter than it normally was. And these are historical observations that were taken with plates or with just people by eye saying, okay, it looks brighter than this star, making an observation of how bright they thought it was. Noticeable brightening here, and then eventually faded. There was another little eruption here. And we think during this eruption, 10 to 20 solar masses of material were ejected. Now, interestingly, Eta Car is not a single star. It is a double star. It's Eta Car A and Eta Car B. B orbits A around every 5 years. It does a complete orbit. It's a very elliptical, weird orbit. And these are two really massive, weird stars, and their winds collide and run into each other. And so it's the most luminous object in the stellar object in the Milky Way. And like I said, we think it's around 120 solar masses, where Eta Car A is maybe 90 solar masses and B is 30 solar masses. And this is a great little chart here. So the sun is this tiny little red dot, and then this is Eta Car A. So that's the comparison in size. And then this is the comparison between A and B. And they're only separated if Eta Car A was at the sun, B would be at Mars. And so at times when the closest passage happens here, Eta Car B actually plows through Eta Car A's atmosphere, we think. And there's crazy X-ray explosions, all kinds of fun stuff happens then. But like clockwork, every 5.5 years there. Okay, so I showed you this here, and we see the great eruption. So some of the stuff I've been working on is trying to figure out how we got to the homunculus nebula and how Eta Car got to be what it is today with the two stars. And so we did some work looking at data of the material around Eta Car, and we came up with this interesting idea that maybe it started out as a triple system, and that's what caused the great eruption, which was the supernova imposter. So I'm going to just run this first, and then we can go through it in a second. So it starts out with two binaries and then a tertiary. So these guys are orbiting, and then this one is orbiting way out. We have an evolution here. The other stars start stripping. And what happens is the mass gets changed. And then at some point, we think there was a star that got thrown out. And then the other star spirals in and then creates this tiny little explosion. And so what's left is, this is beta here. It originally started out as the tertiary companion. It's swapped. And now it's going around at this very weird elliptical orbit. And created this mini explosion that was, 10 to 20 solar masses lost. It was super bright. I'll show this one more time just to see. So this guy is going to end up being our Eta Car B here. And then what happens as normal star A gets stripped. And so during this point, it may have looked brighter. There may have been crazy variability, which we've seen episodes of it being variable in the past. These guys swap, and so when that angular momentum swap happens, basically what it throws the original companion inward, and so those merge into a single star. And that's why it's a super 90 solar mass star here. So this is maybe not exactly what happened, but it's sort of a good idea that is supported by all the observational data that we have on this object. And so this is probably one of the ways we get all of these supernova imposters that we see, and we're going to continue to observe as more and more surveys go on, and we look at the sky nightly in certain areas of the sky and see all these weird transients happening. This is just sort of the graphical version. Like I said, you had these two original stars, the companion, then you switch, the donor gets thrown out, and then you're left with our what's left of Eta Car today. And so I just want to close with, if we're lucky, we may get to see some of these supernova imposters become real supernova in our lifetime. And in fact, there have been some cases where we see outbursts of massive stars, and then a couple of years later, the supernova explodes, or the star fully explodes. And so finding the supernova imposters help us to know where to look, or to keep checking in on these objects to see if they are going to explode anytime soon. But these have all been, other than Eta Car, these have all been supernova in other galaxies. Eta Car is a massive star in our solar system, our Milky Way. And it's possible that it may beat Betelgeuse out and becoming a real supernova first, but we are fully overdue for an actual supernova in the Milky Way. So hopefully that will happen soon. All right.
Okay. All right. Great talk. If you want to unshare, we can start the Q&A.
Yeah. Let's see. Stop share.
So I wanted to ask you some sort of like semi-personal-ish questions as well. And I'll start with a simple one. What got you into astronomy?
I think I think sort of I was always interested, but funnily enough, I got really excited and into physics because I took physics and calculus together my senior year of high school, and I was like, oh my god, it makes sense. Calculus explains physics, and it's like an actual application of the math I'm doing. And you know, I've always been interested in physical sciences, and then astronomy was just my calling, I guess. And so, you know, having great supportive faculty in undergrad, and then wonderful advisors at LSU. I know, Jeff, you're listening. There's your, it's really, really helped. And I think actually in undergrad, there's quite a few women in my undergrad classes. And I think having that group of people that, you know, look similar or, you know, have similar stories, help support you really, really helped.
Yeah, I agree. I had a lot of really good female friends in undergrad, so they were really helpful. So this is getting into the area where it's a little iffy, so you don't have to give any details that you're not comfortable with, but can you tell us, you know, you're switching from a job to another job, and I think that gives you a good viewpoint that a lot of our viewers don't necessarily see a whole lot, which is what is it like sort of transitioning from one astronomy job to another astronomy job?
Yeah, so the application process, especially the higher up you get, is it's a job in itself. And so, you know, you apply for 30 jobs, hope that you might get interviews at 5 and maybe just get one offer. Like that's sort of the number statistics you go for. And there are, you know, a lot of people think that becoming a faculty member is sort of the only way to go as an astronomer, but there's all sorts of other things. And so I'm going from more sort of the university life to a national observatory. So it's going to be really interesting to see how different that works than working at a university. I've been at a university, I guess, since 2005. So this will be interesting. But it's a lot of hard work applying for jobs, and you have to, like, unfortunately, every step of the way from undergrad, grad school, and then any job after, you have to think about what's my endpoint, and everything you do is sort of working for getting that job. So it's probably not unlike any other types of employment, but it's going to be really interesting because one thing they don't tell you is that, yes, you'll be doing science, but you also are going to be your own business manager. You're going to have to, you know, write all of your, like, you have to be a writer, you have to be an accountant, all these things when you work in sciences. It's not just you sitting and doing science all day. I think everyone would be happy if we could do just a fraction of science every day instead of the bureaucracy that we have to do.
Yes, and meetings, of course. More meetings than science.
Right.
And then I'd like to ask you as well, what are your hobbies outside of astronomy as well?
So I've been an old lady since I was like 18. I really like gardening and knitting and quilting. So those are my big things. The cats try to help do all, and some they're a lot more useful in the garden than when I'm knitting, but those are things that I do enjoy, and a lot of reading and things like that. I'm not into the D&D or the Magic the Gathering or the things like that. So maybe my nerd cred will be revoked. But
I now understand why when I turned my computer around earlier, you immediately noticed all the plants.
Yeah. It's been very difficult growing plants in Tucson. It can be done, but it's completely different than in the Southeast, that's for sure.
And then our last sort of like question about you is the age-old, what is your favorite Pokemon?
So I have no idea anything about Pokemon, so I'm picking Oscar the Grouch, even though I know he is not a Pokemon. That is my choice.
All right. You hear that, Jude? It's Oscar the Grouch. Okay, so we'll start with some science questions. A lot of people would like to hear sort of what is happening. You said Eta Car A and Eta Car B, sort of collide. So Eta Car B goes through Eta Car A. Can you just sort of talk about what that looks like? Are they are they going to bump into each other? What does that actually look like in the stars?
Right. So the atmosphere is, fairly extended in Eta Car A. So it's not like, and, of course, stars are not solid things, right? So like your atmosphere, your plasma can move through each other. What's interesting is we've never actually imaged Eta Car B because Eta Car A is so bright. We only know of its existence because of the semi-periodic changes that happen as it revolves around. And we see changes in UV and X-ray excitation, particularly when it plows through, because the winds from both of these stars and from the movement of Eta Car B, they basically run into each other. And when you have this material run into each other, it excites all of the electrons and makes photons, and you get brighter. It doesn't seem like that the whole system brightens every time, but there seems to be some correlation with variability in the optical, particularly variability in the higher, in the UV X-rays and that sort of thing. But in the optical, it's very subtle and you don't see it that much, but there are changes. And unfortunately, you can't really see either of the stars because they're in this dense homunculus nebula. So you have to look at other wavelengths other than optical to even get an idea of what's going on inside there. Yeah. So it's unfortunate that it's just so bright, but also so enshrouded. So it's this weird paradigm, but we have to go on observations from other means to really get an idea of what's going on. Yeah.
Okay. Our next question is from Roger I, and he asks, if mass is added to a red giant, will it reduce back down to its previous incarnation before running out of new hydrogen to fuse and then expand again into a red giant? So if you add hydrogen to a red giant, does it go back to the main sequence?
It won't go back to the main sequence, mainly because you won't be burning hydrogen in the core. You'll be burning hydrogen on the shell. So it could possibly look similar to a main sequence star. Like maybe it will shrink in radius. Maybe it'll be a yellow color instead of a red or a blue. But eventually that hydrogen is going to burn quickly on the surface as a shell, and then you'll have the other core exposed. So it won't ever go back, but it'll just look weird. And that period of time is so fast that we don't have observational evidence of these, a lot of observational evidence, because it's so quick and they're less massive stars than just regular sun-sized stars. So being able to observationally see that is difficult. You have to get lucky.
Rob Parks asks, on what time scale does the infall of the third star cause the situation which created the homunculus cloud?
Right. Yes. So that little video should not be taken as gospel. But we think that the time scale is probably over only hundreds of years, because there are previous eruptions, we think every 200 years, that can sort of be mapped out to around, there's at least one in 1200, 1400, 1600, 1800. They're smaller eruptions. And that's been figured out by looking at HST and plate images and basically taking material that's been ejected and moving it back in time and tracing when it must have been ejected. And so we think that the in-spiral must have happened maybe within the last 1,000 years. It got at least started, and that the actual final transfer and merger happened during the Great Eruption. But we are not theorists, we are not modelers. We're just using observational data and saying this is an idea that could explain what we're seeing now.
Okay. Melissa Porter asks, what is your favorite galaxy?
NGC 6946. It is the fireworks galaxy. It is a beautiful face-on spiral, and it's had at least 10 supernova imposters in the past in the past 100 years. We usually have a supernova in a galaxy like that every 100 years. This one has had 10. So it's really exciting, and we always have lots of great data on the galaxy.
I'm very glad that the Pokemon question, no answer. Galaxy?
Okay, I guess that gets me my nerd cred back.
right there. And then Stephen Dorsher also asks, do you get to keep your code and your research when you switch to a new job in general?
Yeah. So, I mean, I guess it sort of depends on how your job is moving. So the job that I'm moving to will be half service and half research. So the half of my time that I'm doing research, I'll get to keep all of my data, all of my collaborators, hopefully get new collaborators. But the other half I will be spending actually in support of the telescope. So I will be observing or helping plan observing runs or interacting with people in the community who have observing time coming up and helping them plan the runs they want to do. So I'm super excited about that. I love observing. I spend lots of time in the telescope. And so that's really great. And yes, I could take my codes, but I am not a very prolific coder. so I guess a couple of IRAF scripts and a Python notebook is going with me.
The other day I was in a meeting and a coder asked me about my code and I was like, I'm not good at coding. Please don't look at my code anymore. So
technically this is my code. I notebook everything. Everything is in beautiful notebooks, handwritten. And so even to this day, people will call me and ask for something they know I've written in my notebook like a decade ago. And I'm ready. I'm very analog and old school.
You alluded to this in your talk, but I wanted to ask you how you felt about the Betelgeuse discourse.
I think I was as enthralled as anyone because you're so used to looking up and seeing Betelgeuse and noticing the big red star in Orion, and then it just wasn't there for months. So I still don't know how I don't know if I've been reading, their new papers come out all the time as to whether it's a dust thing or if it's a big convective cell where it's cooler or whatever. We know that Betelgeuse is going to explode at some point. It's a red supergiant. We also know that it appears to be a single star, so it's not going to have any weird binary interaction. It shouldn't have like a supernova imposter before it goes off. But yeah, I mean, I think it's just really interesting to be able to watch red supergiant evolution in real time and sort of see what's going on. So it's always nice to have that laboratory, right in our backyard. But yes, it will explode today, maybe a million years, maybe it'll happen at some point.
Any day now on an astronomical time scale.
Right, exactly. But if it happened today, it would have actually exploded in around 14 AD. So that's kind of cool to think that the light travel time it would take to get here.
And then I wanted to ask you one more question, which is something that I've always wondered, which is there a difference between a supernova that would collapse into a black hole versus one that would collapse into a neutron star?
That is a question we are still trying to answer. So it started out thinking was, okay, if a star if it was on the main sequence at a certain mass, like say anything under 20 solar masses would just become neutron stars. Anything more massive would collapse straight into a black hole. But now we're finding as cirrus modelers are going through these islands of explodability, like maybe a star that's 8 to 15 solar masses makes a neutron star, but maybe 15 to 20 goes straight to black hole, but then 20 to 25, maybe that's a neutron star. So we don't really have an answer. I am involved in a program, though, which is really exciting to look for failed supernova. So we're looking at past images taken with HST to see a star blink out and hopefully determine if that was a failed supernova and then get an idea of the mass of that star so we can add observational data to the theoretical data to help figure out what's going on. The problem is a lot of these are in binaries. And so when you have two stars interacting, it completely throws off the type of modeling you do when you just have a single star minding its own business by itself. So that's what makes it difficult to decide if there is a direct mass to remnant equation, which there doesn't seem to be yet.
All righty. Okay. If Abby wants to come back on, she can, but she's not required to. So thank you all to everyone who is watching. And I wanted to thank both of our speakers for wonderful talks and have your beautiful faces here. We know that you're both really busy, so we're very happy to have you here. I wanted to also shout out our two streamers, Allie and Alex, who are behind the scenes They work really hard to put this show on for us, and they always do. But before we head out, I wanted to mention just a few more things before we close out. So if you're watching us asynchronously, which I know a lot of you do, feel free to still interact with the video, give us a like, subscribe to our YouTube, reach out to our social media. All of that jazz is great. I do believe we did actually hit our 100 subscriber thing, so we will have a unique YouTube link soon, so that's very exciting. Definitely consider donating as well. That helps us to just put on all of our shows and give little gifts to our speakers whenever they're done speaking. So keep an eye on our Facebook, Instagram, and Twitter, where we'll post information about all of our events as soon as we have it. And we will see you all here on YouTube next month, where we'll have 2 more lovely speakers for you. And then we all wave like Muppets because we recorded.
Yay! Bye.